My talk is titled Variable Blue Straggler Stars in the Open Cluster NGC 6819 observed in the Kepler Superstamp field. NGC 6819 is a relatively faint open cluster in the constellation Cygnus. It was discovered by Caroline Herschel in 1784. It is around 8,000 light years away. The cluster age is 2.4 billion years, so it's almost exactly a little more than half the age of our sun. The brightest stars in the cluster are 10th to 12th magnitude, and these are the red giant stars in the cluster. So why are we interested in this particular cluster and in open clusters in general? Well, these are important objects for improving our knowledge of stellar structure and stellar evolution. All cluster members should have formed together and therefore should have a common age and initial element abundances. And knowing these two things, the age and the metallicity, or the amount of heavy elements in the star's makeup, gives us additional key constraints for stellar evolution models and astroseismology. NGC 6819 is of special interest because it contains a number of blue stragglers. These are stars that are bluer and hotter than the cluster main sequence turnoff. So on the left, you see a Hertzsprung-Russell diagram, or actually a color magnitude diagram in this case, showing the stars that are in the colored symbols that are in the cluster NGC 6819. So stars along this line right here are on the main sequence burning hydrogen into helium in their cores. And when they exhaust the core hydrogen, the stars evolve off the main sequence off to the right here and become red giant stars. But you see in this cluster, there are a number of stars circled by this blue oval that haven't evolved off the main sequence like they should have. They're still sitting here above the main sequence. So why are these stars still here? Their origin is not known. These are the blue stragglers. They may have originated because of mass transfer, adding more material to the star, or a binary merger. And there's a third possibility that extra mixing in the core of the star rejuvenated the star and mixed some extra hydrogen into the core, so that kept it alive longer. But that theory is a little less favored, well, quite a bit less favored than the first two. And many of these stars, because of the age of this cluster, are in exactly the right place to be delta Scuti pulsating variable stars. And if we can measure the frequencies of the pulsations, those may help us determine the origin of these blue stragglers. So why do we care about pulsations? Well, they give us information about the sun, about distant stars and planets that we could not obtain otherwise from just the light output or the spectra alone. So they will tell us, if we can decipher them, what is going on inside the star where we can't see. What is the mass and radius of the star? By looking at properties of the frequencies or period spacings, we can, and comparing with stellar models, we can infer the mass and radius of the star. We can tell, because if we find the radius of the star, how large a transiting planet is that might be orbiting the star and seen as it goes in front of the star and occults some of the light. So then if we know the radius of the star, we can scale and find the mass of the planet. And then we can also find out what the age of the star is, again, by using stellar models in conjunction with the pulsation frequencies. So I'm going to tell you here a little bit about Gamma Doradus and Delta Scuti variable stars. These are both stars that, like the sun, are main sequence stars. They are burning hydrogen into helium in their cores, and they also pulsate. In the sun's case, I would say more oscillate in many modes simultaneously. So here's a log luminosity versus log effective temperature diagram showing different types of variable stars on the main sequence. And you see the sun is down here in this yellow oval among the sun-like oscillators. The Gamma Doradus stars are a little bit higher in mass and luminosity, a little bit hotter in temperature, and the Delta Scuti variables are a little bit hotter still, and a little bit more massive, and they overlap with the Gamma Dor stars a little bit. So the Delta Scuti stars are about twice the mass of the sun. They pulsate using in pressure modes or acoustic modes, sound modes. Their periods are around 2 hours. Their frequencies, 1 over the period and converting to days, are around 12 cycles per day. The Gamma Dorada stars are about 1.5 times the mass of the sun. They pulsate in gravity mode pulsations. So gravity instead of pressure is the restoring force for those modes. And their periods are longer, around 1 day. Frequencies are seen between about 0.3 and 3 cycles per day. This picture is meant to illustrate with an analogy how stars pulsate and why they pulsate. And they pulsate in a very similar way to this bell that I'm showing in this picture. So on the left, you see a picture of a bell, and when you ring the bell, using the ringer here, it can vibrate in many resonant frequencies at the same time, many overtones, many harmonics at the same time. Certain ones fit the shape of the bell the best. So this is a low frequency mode at 1300 hertz. And this Dopplergram image is showing the vibrations at this frequency. So you see patches on the bell are vibrating in and out with that frequency, and there are node lines where the bell is not vibrating. That part of the surface is staying still, and these are going in and out opposite or together. So if you go up to a higher frequency resonant mode in this bell, you see these patches get closer together. There are more node lines. This is about a 1470 hertz mode. And then you can see an even higher frequency mode here with more of these patches of vibrating in and out and more closely spaced lines, node lines. So just like this bell, the sun and other stars pulsate in many non-radial and radial modes simultaneously. And for the sun, we can detect modes that have numbers of node lines on the surface that actually would go all the way up to 1,000 lines. So, and that's because we can resolve the disk of the sun. We're so close we can compare different patches in radial velocity and see them vibrating up and down and do an analysis like was done with that bell to determine all the different frequencies. But for distant stars, we can't resolve the surface. It just looks like a point source. So we're only able to detect modes where the oscillations don't average out over the entire disk. So we could detect modes of degree L of 0, which is a radial pulsation, L of 1, L of 2, and maybe even higher, L of 3, maybe up to L of 10. It's to be determined how far we can go with the precision of photometry, looking at patches getting brighter and dimmer and correspondingly changing temperature. It's why the star is becoming brighter and dimmer with time and enabling us to detect these modes at different frequencies. So we can expect to find modes of degree L of 0, 1, or 2 on distant stars. So now I'm going to tell you a little bit about the NASA Kepler mission. It was launched in March of 2009. The mission ended in 2018, and it used high precision CCD photometry to search for planetary transits and find planets orbiting distant stars. It had a secondary mission to survey and monitor for variability over 100,000 stars, and then to use this to find oscillation modes, pulsation modes, and do astroseismology. This is a field of study using waves and vibrations on stars to infer the star's internal structure. So this is a picture of the Kepler CCD array, the 21 CCDs mounted after assembly of this part of the spacecraft. I should back up and tell you that for the first 4 years, the Kepler spacecraft was pointing in this one particular field of view here in the Cygnus Lyra region of the sky. And you can see the 21 CCD modules right here that were fixed on that particular spot. So there's the CCD array. Here, the array is up here on the telescope, and it's getting mounted to the third stage. And Kepler was launched not around Earth orbit, but it's in a solar orbit and trailing the Earth. So this allowed it to view continuously this patch of the sky without any obstruction by Earth as it would orbit around, and the Earth would obscure part of the sky. It could actually look, because it was in an orbit around the sun, gradually getting further away at the same patch of sky for a very long time. So for the first 4 years of its mission, Kepler was looking, as I said, at this patch between Cygnus and Lyra. And here is the cluster we were interested in, NGC 6819, down here in this CCD module. So it was observed for 4 years continuously. So how was it observed, and what kind of data was taken? Well, there was a 200 by 200 pixel array set aside called a Superstamp, and that's centered on the center of the cluster. It didn't include the entire cluster, just the dense central part. And it took data continuously, except there were some 90-day gaps because 2 of the CCD modules failed during the course of the 4-year mission. So there were some gaps in that continuous coverage. It took 1 data point integrating on the light every 30 minutes. So it's a 30-minute cadence. And then it recorded that data for all 200 pixels and then sent it back to the Earth for processing. And you notice this field is very crowded. So these pixels are 4 by 4 arc seconds, and sometimes more than one star can be in 1 pixel, and sometimes even nearby pixels can put light into a pixel and contaminate the light curve. So this is an issue that needs to be dealt with, and I'll show you an example later. And the cluster membership was determined using Gaia early data release 3 astrometry. So using proper motions and parallax measurements by the Gaia spacecraft. So now I'm going to show you some results from the stars we looked at that are in the blue straggler region. This is Kepler input catalog 5024468, and it's the brightest of the stars I'm going to show you, magnitude 12.8. The effective temperature is 7,000 Kelvin. That is right in the right location to be a delta Scuti variable star. This is a zoom in on a 5-day portion of the light curve. So the points are the data points every 30 minutes, and then I've connected them with a little blue thin line here. So you see there's an envelope of oscillation here where many modes are beating against each other constructively and destructively to make this light curve pattern. And if you do a Fourier analysis on the 4-year light curve, you see there are a lot of frequencies here, right around 12 cycles per day. And that's exactly what we expected for a delta Scuti variable. 2 hours is 12 cycles per day. And you can pre-whiten this amplitude spectrum by successively removing the highest frequency mode and then looking at what's left and comparing it with the noise level. And my collaborators found 236 frequencies in this star with signal to noise greater than 6. They did have to remove contamination from a binary that I'm going to show you next. This star actually was known as a delta Scuti variable before the Kepler mission, published by Talamantes et al. In 2010. So you can zoom in also on this amplitude spectrum and see that there even are some low frequency modes that are close to the Gamma Doradus variable star frequency range here, 2, 3, 4 cycles per day. So if these modes are real, confirmed, and to be pulsations and not something else like rotation or star spots, this star would actually be a Gamma Dora Delta Scuti hybrid variable. Now I'm showing you the light curve of a nearby eclipsing binary, right here, KIC 24450, and this star is actually contaminating the light curve from the star I just showed you, and vice versa also happens. The delta Scuti frequencies are contaminating this particular light curve. So this is a 5-day zoom in, and you can see the eclipses here on this binary, a very narrow eclipse every 3.5 day period. 2 of these make up a full period. And if you do a Fourier analysis of this, you see this cone-like spectrum that is the result of the binary, but you can also see these delta Scuti modes are contaminating this light curve. So this has to be looked for, checked whenever you're doing analysis of the photometry in the crowded field. Here's the second star I'm going to talk to you about, KIC 5024084. It's also about 15th magnitude, quite a bit cooler, 6,500 K. It is in the blue straggler region for this cluster. You can see here a zoom in, a 50-day zoom in this case, on the light curve. So the variability time scale is longer in the star. The up and down motions take longer. And if we do a Fourier analysis on this light curve for the whole 4 years, we find a lot of modes around 0.5, 1 cycle per day. This is exactly what we expect for gamma Doradus pulsating variables. We also took a look at very high frequencies here, and we did find one mode in the delta Scuti frequency range. And if this mode is confirmed, this star also could be a hybrid variable, but with just one mode, it's rather tentative to say whether we would call it a hybrid. Bologna et al. Had looked at this star with an early selection of Kepler data and found a 2.07 day period and suggested that this was a rotation period of the star and that the variability was being caused by star spots. And this group also thought that the star spots could be rotating at different rates, just like our sun rotates faster at the equator than near the poles. And this variability at different frequencies could be caused by differential rotation. We didn't find a 2.07 day period. We have 2 peaks at a little bit lower frequency. So it remains to be seen whether rotation and star spots are causing all of the variability or whether gamma Dora pulsations are also responsible. So this is the third star that's in the blue straggler region, also about 15th magnitude, temperature in between the previous 2 blue straggler stars I showed you. This is a 20-day zoom in of the light curve, and the Fourier analysis reveals a lot of low frequency modes, again, just the right frequencies to be gamma Doradus type pulsations. We did not find any higher frequency pulsations in this star, but there are 84 of them with signal to noise greater than 8. Milliman et al. Looked at this star in spectroscopy and found that it was a single line spectroscopic binary with a period of 762 days, so not quite 2 Earth years. So this binary companion hasn't been characterized or seen, so that would be an interesting follow-up project to see if we can find, confirm, identify a possible binary and whether that binary companion has any influence on the pulsations. So this is a 4th blue straggler, also 15th magnitude. This is the hottest of the stars I'm going to show you, 7,300 K. It has, this is a 10-day picture of the light curve, of the 4-year light curve zoom in. And you can see there's this kind of long period modulation here on top of some very high frequency modulation going on. So if we zoom in on it, again, this is a 2-day zoom in, you can see the high frequencies right here. And if we do a Fourier analysis of this, we see a few of those low frequencies that are characteristic of this longer modulation. And then we see a lot of frequencies between 10 and even higher, up to 25 cycles per day. And these are the delta Scuti pulsation modes. There's lots of them, 124 frequencies found. Now, this star illustrates a problem with 30-minute cadence data. If it's equally spaced, there is a Nyquist frequency limit of 24 cycles per day, above which the frequencies get reflected. And these are actually aliases reflected about that 24 cycle per day Nyquist frequency. So most of these frequencies are aliases, but because the data set for Kepler was so long and Earth was getting further and further ahead of the spacecraft, this difference in light travel time could break this degeneracy, and it makes it not quite 30 minutes space data as you go out in time. And we can actually determine whether any of these higher frequencies are real or rather only Nyquist reflections. So if they are Nyquist reflections, they will have a lower amplitude. So you see this one has a lower amplitude than that one. So this is the real frequency. But there are some frequencies in this clump here where the amplitude is actually higher than the one on the other side, the reflection. So there are some real frequencies above 24 cycles per day in this hot Delta Scuti star. So this is my final star. This star had some variability in the range we're looking for, but it turned out not to be a pulsating variable. This star is closer to the main sequence turnoff. It's a little bit cooler than the sun, 5493 Kelvin. And it only showed, well, first it showed variability. It looks like a couple of modes beating against each other. This is a 5-day zoom in. But if you do a Fourier analysis of this, you only find 2 modes and their harmonics. We found 6 harmonics of one of the modes and 9 harmonics of the other. It's not really understood why the lowest frequency modes have also a low amplitude. I would have expected these to have a higher amplitude and then the amplitudes to gradually go down with the successive harmonics. But this is not the case for the star. We need to understand what's going on, take a lot more time to understand what's going on here. Gosnell et al. In 2012 looked at the star in UV and X-ray and found that it was an active X-ray binary and suggested that it was an RS-CVN star, which is a star that shows chromospheric activity, rotation, and spots that may be responsible for some of this modulation. The binary orbits may be responsible for some of this modulation. So a lot more needs to be understood. So this is a picture from Gosnell et al. Color magnitude diagram showing the star X9, right here, the X-ray binary. And you see it's not quite at the main sequence turnoff, a little bit cooler, a little bit lower magnitude than the main sequence turnoff. So here are my conclusions. Despite being in the same cluster, having similar location in the HR diagram, the light curves of each of these stars have their own personality. They're very different from each other. Of the 5 cluster members, we found 2 Delta Scuti stars, and they may be Delta Scuti Gamma Dor hybrids, 2 stars with lower frequency variability that are likely to be Gamma Dor pulsators, and they may also show global Rossby modes, which are in the same frequency range as Gamma Dor stars, but they may also, or instead, be showing rotation and spots, maybe even differential rotation with spots rotating at different rates. So that needs to be sorted out for these stars. And we found 1 star that shows only these 2 close frequencies and their harmonics. So for future work, we'd like to examine the frequency or period spacings of these stars, which are often used to figure out the stellar mean density and the internal rotation rate in using astroseismic techniques. We'd like to model the evolution and pulsation taking into account the cluster constraints of the age and the common metallicity, and find out if we can gain any insight into the origin of the blue stragglers in this cluster. And finally, more data would be useful. Spectroscopy to help sort out pulsations versus star spots, color time series to help with mode identification, more photometry, also to see if things are changing with time in these stars after the Kepler data was taken. It ended in 2014, something like that. It ended quite a while ago. So maybe things have changed and evolved in these stars since then. Okay, thank you for your attention.
All right, questions? Oh. Looks like everyone needs more coffee.
I got her. 1 second. The spotlight. We'll make it so we can see her. So.
Can you hear me?
Oh, it looks like Ron has a question.
Hi, Joyce. My name is Woody Sims. Can you hear me?
Yes, I can hear you. Can you hear me?
Yes, thank
Okay.
you. I noticed on all your plots where you showed us 5 or 10 or 20 days, maybe on the left-hand plot, and then you had the frequency distributions on the right. Were those results on just the data set that you showed on the left, that number of days, or was it on multiple years worth of data?
Yes, the Fourier analysis was done using the entire 4 years of data. So I was just zooming in so you could see some features in the light curve, because otherwise it's all just smashed together and all you see is lines going up and down with nothing. You can't resolve anything. So yeah, no, the Fourier analysis is done using all of the data.
Ron, you have a question? You have your hand up? Do you want to unmute yourself?
Sure. Thank you very much. It's very interesting. Your comments are indicating that you were hoping for some spectroscopic collaboration, or what would you consider to be an accurate enough spectrographic reading for you? As these seem to be all around 15th magnitude, very tight fields, correct?
Correct. Yes. So it's my collaborators right now are just both at New Mexico State and in Europe have a couple of just single spectra they've taken, and they're trying to just look at them and verify the temperatures and the log surface gravities. And they're having a hard enough time with that, trying to come up with reasonable results. So just taking a spectra and seeing if we can, and also the metallicity. It seems like even though these stars in this cluster should all have the same metallicity, the measurements of different stars, even in different evolutionary states, are not very tight. There's quite a range. And does that mean that evolution has changed the metallicities, or are they just that uncertain because it's hard to do the analysis? So beyond that, I would say doing some time series spectroscopy, trying to find out about pulsations versus star spots would be useful, and also maybe some spectra spaced several years apart to look at the possible binary orbits, companions of a couple of the stars would be interesting.
What kind of resolution are you hoping for?
Oh, good question. I am not a spectroscopist, so I can't tell you exactly. I think the higher resolution, the better. If you want to look at line profile variations, for example, or measure radial velocities, I think you would need fairly high resolution.
So we're looking at some of the larger telescopes that we might have, correct?
Yeah, I think so. Some of the larger ones, but I don't think it's out of the possibility of amateurs to do this.
Okay, I would say, Joyce, I would say probably most of us are 0.4 meters or less. You know, I wonder if this would be of any assistance to you.
Sure. I don't know about with spectroscopy on that. With that, I suppose photometry, in addition to look at whether these modes we're seeing, the highest amplitude modes, are changing in amplitude, or different frequencies are coming in while some of them are dying down. That would be an interesting project as well. So photometry would be useful too. So I guess I need to talk to you guys, the experts there, about what you could do, because I honestly am not a spectroscopist and I don't know.
Well, thank you, Joyce. That helps. Thank you.
Any other questions? No. All right. Thank you, Joyce, so much. Oh, wait, is there one more question? Oh, online. Okay. Larry, if you unmute yourself.
It's not working. Okay, there we go. Does that work?
Yes.
Okay. I'm just wondering, what are the proposed formation scenarios for blue stragglers in such a diffuse kind of environment. I've heard of them in globular clusters where they're much more compact and interactions are much more likely. An open cluster like this, what are the kinds of things that could happen here?
Right, that is the question we're really interested in. There are blue stragglers in open clusters. This cluster, I like it because it has the particular age of it puts the Delta Scuti stars in the blue straggler region pretty well. So we have a lot of pulsating blue stragglers, and that might help us figure out what's going on inside. So still the leading hypotheses are, if you can't find a binary companion, it has to have merged in the past, right? So some kind of binary merger. If you do see a companion, then you can think about, well, was there some mass transfer event in the past? So those are two possibilities. And when I was in grad school, we were always thinking we don't understand convection and mixing processes in stars. And maybe there is some trigger internally that was causing a mixing episode that would rejuvenate the star. And that's not a favored hypothesis anymore, but if we can't find a companion and the merger scenario doesn't look like it's working in terms of the astroseismology and what the internal structure looks like, we may have to go back and look at some things like that. But I'm really interested in trying to model, what does a star look like? What does the inside look like after it's merged? Can we do the hydrodynamic calculations today that we couldn't do 30 years ago when I was in school, to look at a binary merger and see what the composition gradients are in this inside after it's settled down, and whether that particular structure would give us the pulsations we see.
Okay, thank you.
Okay, thank you, Joyce.